Alrighty. So before this, we talked about thermochem, the study between energy and chemistry, and defined energy. How does the heat and work that's transferred between objects? And we think of energy that's kind of a property of objects and different types of energy, and how using system and surroundings to define what you're looking at can help look at the energy flow. And then we talked about the different units. So all of that kind of brings us up to thermodynamics. So what is thermodynamics? How is it different than thermochemistry? So thermodynamics is the study of energy and its interconversion. So how the energy is converting in different ways. And the first law of thermodynamics is the law of energy conservation. So the total energy of the universe is constant. So this is why the energy of the system plus the energy of the surroundings is equal to 0 because it's constant, it's conserved. Therefore, energy and system, the amount of energy in the system, the magnitude is the same, and the sign is always different. One is absorbed, the other one is lost, and vice versa. So the total amount of kinetic and potential energy a system possesses is defined through internal energy. So this is, for thermodynamics, that study of energy is internal energy, which is delta E. And it's the total amount of kinetic energy and potential energy a system possesses So any system, all of its potential and kinetic energy are summed together, and that defines its internal energy. So internal energy is dependent upon conditions of final and initial, kind of where the system ended up from where it started. That's internal energy. That's what makes internal energy a state function, which is the result because it only depends on initial and final conditions. It doesn't depend on the process, the pathway that was used to get there. So, in other words, since energy is neither created nor destroyed, and since the universe does not exchange energy with anything else, its energy content does not change. So the first law has many implications, and the most important one is that with energy, you cannot get something for nothing. The best way you can do anything with energy is to break even. According to the first law, a device that would continually produce energy with no energy input cannot exist. So something can only exist giving off energy if it continually is also gaining in energy. There's constantly an input of energy. So the internal energy is the sum of the kinetic and the potential energy, and we think of it as a state function. Now let's look at specifically what I mean when I say state function. So think of going on a hike, right? And you have two pathways. So pathway A is going along nice and slow. It's a little bit more flat. Just takes a little bit longer to get there. Pathway B is you just take the steepest part of the hill and get up. Now, you start at the same point. Both people are starting at 0 feet. And then at the end, you're both at 10,000. Now, path B was only 5 miles because you went steeper and you weren't going as long. And path A was 12 miles because you took kind of more of the less steep path length. However, in the end, you had the same final results and initial result. You started at 0 and ended at 10. That is a state function. So it depends only on the difference between initial and final states, not on the path taken. So we think of internal energy as the difference between the final energy and its initial energy. And you can think of the energy of a reaction as the energy between the products and reactants difference. That tells us the amount of energy that was conserved, the sum of the potential and kinetic energy. So, for example, if you were to look at a reaction between carbon and oxygen to form carbon dioxide, just as we portray the changes that occur when climbing a mountain with an altitude diagram that shows at the altitude before and after the climb, we can portray the energy change that occurred during a reaction with an energy diagram, which compares the internal energy of the reactant. So for example, I can make a little diagram just like I showed you, that hill example that kind of showed the amount of energy that was being gained and lost. So here, if I have my internal energy, I have my reactants, and then I have my products. And I want you to think, why am I putting the reactants higher up than the products? Well, the reactants have to gain energy in order to form the products. To form carbon dioxide, it looks like this, right? That's the Lewis structure. And we know oxygen has a double bond, and carbon has all these singles. Well, in order for oxygen to bond together with carbon, it needs to break its double bond and then form its electron bonding with carbon. So in order for that to happen, it needs energy. So the reactants absorb energy, and the products then come together and release that excess amount of energy. So reactants are higher up, and products are lower down when in the end you release energy. Now I want you to note that that's different if energy is absorbed rather than released. So endothermic and exothermic reaction. Here, energy is released by forming carbon dioxide. So the vertical axis of the diagram is the internal energy, which increases as we move up on the diagram. For this reaction, the reactants are higher on the diagram than the products because they have internal energy. As the reaction occurs, the reactants become products, which have lower internal energy. And therefore, energy is given off by the reaction, and your delta E, right, your change in energy is negative. So we know energy is given off, and your change in energy is negative. So where does the energy lost by the reactants as they transform to products go? So if we define thermodynamics system as the reactants and products of the reaction, then the energy flow out of the system and into the surroundings. So again, we're defining that the system is the reactants and the products. So then the flow is that the energy went from this out of the system into the surroundings because the energy was releasing for the total reaction, so it went out of the surroundings. So that means that the system is negative and the surroundings is positive. And according to the first law of energy, must be conserved. So therefore, the amount of energy lost by the system must equal the amount of energy gained by the surroundings. They have to be inverse of each other. So I'm saying that my reactants and products are my systems, right? And the energy flows out of the system and into the surroundings because, as you can see, as my reactants form my products, energy was released. So it flows out of the system. And it doesn't just go anywhere, it goes into the surroundings of the reaction. Let's think of another way to look at that. So the energy level diagram is nearly identical when we look at the reverse reaction of carbon dioxide. So if we were to look at CO2, decomposition reaction to carbon solid and oxygen gas. So here, if I draw my diagram, my reactants are going to be on the bottom. My products are going to be on the top. And my energy change actually goes up. So the energy level diagram is almost identical, but the important difference is that carbon dioxide is now the reactant and carbon and oxygen are the products. So instead of decreasing in energy as the reaction occurs, the system increases in energy. So you have a positive change in energy. So in this reverse reaction, your change in energy is positive, and the energy flow is then into the system. So it's an endothermic reaction, and energy goes into the systems from the surroundings. So therefore, your delta E system is positive, and your surroundings is negative. So summarizing that energy flow, if the reactants have a higher internal energy than the products, the system is negative, and therefore energy flows out of the system into the surroundings. If the reactants have a lower internal energy than the products, the change in energy of the system is positive, and energy flows into the system from the surroundings. And we can think of the internal energy of the system just the same way that we think about the balance in a checking account. Energy flows out of the system like a withdrawal, and therefore carries a negative sign. Energy flowing into the system is like a deposit, and therefore has a positive sign. So you can kind of think of it when you put money in your account. When you take it out, it shows you a minus sign, right? And when you put it in, it shows a positive sign of energy. So this brings us up to heat and work. So these are the two really big important components of energy. We already slowly defined them, and now with everything that we talked about, we're going to put it back together. So we already discussed that a system can exchange energy with its surroundings through heat and work. And according to the first law of thermodynamics, the change in the internal energy of the system is the sum of the heat transferred and work done. So we think that delta E is equal to Q plus W, where we define the system and we think of the sign of heat work to figure out the sign of the internal energy. So we follow the standard convention of the internal energy, and we think of the system. So energy entering the system through heat and work carries a positive sign, and energy leaving the system through heat and work carries a negative sign. So we can define our system as previously discussed, just like the billiard ball example. So first, let's see. We know that this is positive when energy is going into the system. And internal energy is negative when energy is going out of the system. Now, I want you to take a moment, maybe even pause the video, to think of what heat and work would have to be to have a positive energy or negative energy. So, in order for energy to flow into the system, your heat has to be positive, and your work has to be positive. And what it means for your heat to be positive is that the system, does it gain or lose heat? What do you think? It gains heat, thermal energy. Gains thermal energy, right? The energy in form of heat, temperature related. What about work? Is work being done on the system, or is it being not done? When work is positive, work is done on the system by the surroundings. So let's think of when energy flows out of the system. Your heat is negative and work is negative. So when your heat is negative, what happens to the system? System loses thermal energy, loses heat. What about work? What's work when it's negative? When work is negative, work is done by the system. So when the system's actually doing the work, it's a negative relationship. So back to our little billiard ball example here. So the rolling ball has a certain amount of initial kinetic energy, right? So we have that silver ball and the purple ball, and we know that we hit the silver ball to go at a certain speed, and eventually it hits that purple ball, and the purple ball moves. So initially, it has a certain amount of kinetic energy. And when it reaches the other end of the table, the silver rolling ball collides head-on with a second ball. Assume that the first ball loses all of its kinetic energy so that it remains completely still. So if this ball has a certain amount of kinetic energy and it's traveling at this distance, the work uses to transfer its energy to the purple ball. Now the silver ball completely remains still and the purple one moves. The total change in internal energy for the first ball is therefore the difference between the initial kinetic energy and its final kinetic energy. So its initial kinetic energy was 5 joules, right? Now, if it's staying still like this, what is its final kinetic energy? 0. So then the total kinetic energy change would be 5. So the first billiard ball lost all of its energy. What happened to that energy? So since it's staying completely still, where did the energy go? According to the first law, it must have been transferred to the surroundings. In fact, the energy lost by the system must exactly equal the amount of gained by the surroundings. The surroundings include both the pool table and the second ball. So just because the purple ball moved, it doesn't mean that it took all of the energy of the silver ball. Since the silver ball is a system, it transferred its energy to the surroundings, and the surroundings can be multiple things. So it's the pool table, since it's on the pool table, and it's hitting that second ball. So the pool table absorbs some of the ball's kinetic energy as the ball rolls down the table. So as it goes down, some of the heat is lost, and let's say that that's 0.5, and the pool table absorbing that 0.5. Little minute bumps on the table surface can cause friction, which slows the ball down by converting the kinetic energy to heat. And then the second ball, some of the balls, absorbs its kinetic energy by converting it from work. So basically, through the friction of a table, the energy is lost through heat. And as that ball hits the other ball, the energy is absorbed through work because it's that force through a distance. So even though it's always the case that the system and the surroundings have to be completely inverse, the exact amount of work done on the second ball depends on the quantity of the billiard table. So that can depend on kind of the pathway to get there. So a smooth table, most of the first ball internal kinetic energy is transferred to the second ball as work, right? Because there's not really anything getting in the way. But what about if we think of a rough table? So it's a little hard to see, but imagine that this was kind of a rough table. So on a rough table, we still have the same amount of kinetic energy, but because there's a lot of friction as the ball moves, a lot of heat is lost. So less work can be transferred, and the amount of kinetic energy transferred to the second ball is less. So notice that the respective amounts of energy converted to heat and work depend on the details of the pool table and the path taken. So it really depends on how the first ball got to the second ball. Either through a smooth table, a lot of the energy was transferred, or a rough table, only a little amount of energy was transferred. So it means that the conditions that heat and work are in are really dependent on their signs. This is different than internal energy. Internal energy just depends on the final and the initial states. So that means that heat and work are actually path dependent. they're going to change. Their values are going to be different based off of the path that they took. So less heat would be lost if it was a smooth table, and more work would be transferred because the smoothness of the table can cause the speed of the ball to be higher to transfer more work. But if it's a rough table, there's more friction, so the ball is working a little bit harder in its energy, so more heat is being lost as thermal energy, and less work is available in the end to transfer towards the second ball. Now, heat and work depend on the details of the pool and table and the path taken, while the change in internal energy of the rolling ball does not. Because internal energy is a state function, the value of the internal energy for the process in which the ball moves across the table and collides with the other ball depends only on the ball's initial and final values of kinetic energy. Work and heat, though, are not state functions. The values of heat and work depend on the details of the ball's journey across the table. The smooth table, work is greater in magnitude than Q because more was transferred. On the rough table, Q is way greater, right? 3 joules is higher than 2 joules. However, the sum, the internal energy, is just the sum of both of them, which is constant. So it's still that 5 joules in the end. It doesn't matter the path that it took to get there. Let's take a moment to look at this practice. So identify each energy exchange as primarily heat or work and determine whether the sign of the internal energy is positive or negative. Sweat evaporates from your skin, cooling the skin, and sweat is the system. Would this be heat or work? This would be heat, right? Because it's talking about temperature, so it's heat. A balloon expands against an external pressure. Contents of the balloon is the system. So a balloon expanding, right? That's a force going through a distance, so that's work. An aqueous chemical reaction mixture is warmed with an external flame. The reaction mixture is the system. This is also an example of heat. So now on your own, I want you to define which would be positive and which would be negative. So now what I'd like to do is do an example of internal energy. The gas in a piston warms and absorbs 655 joules of heat. So that means 655 joules of heat is my Q. The expansion performs 345 joules of work on the surroundings. So work is 345 joules. What is the change in energy of the system? So my change in internal energy is heat and work, summed together. So what I need to think of is, are any of these values going to be positive or negative, or are they already the way that they need to be? Well, my heat is absorbing, so the heat is going to stay positive. And the work is the expansion performs 344 joules of work on the surroundings. So the system is doing the work. So when the system is doing the work, is it positive or negative? It's negative, right? When system is doing the work, it is negative. Work done by the system is negative. So therefore, we would have 655 joules minus 344, which is equal to 311 joules of energy in the end of this reaction. Heat and work. So now we're going to quantify heat and work a little bit. Heat is a transfer thermal energy. And we discussed that thermal energy always flows from matter at a higher temperature to matter at a lower temperature. If you have your hot coffee and think of just like the hot coffee in the pot, and you pour that hot pot of coffee into your mug. Now, the mug cools down, right? The mug warms up as the coffee begins to cool down. It's not the other way around. The thermal energy always goes from a matter at higher temperature to a matter of lower temperature. Another example of this would be like an ice cube in your hand. So if you put an ice cube in your hand, after a while the ice cube begins to melt. That's because the ice cube is taking in the heat, right, from the higher temperature of your hand to then go to the lower temperature of the ice to begin to melt it. So the thermal energy in the molecules that compose the hot coffee, what they do is they distribute themselves to the molecules in the surroundings. So as you pour your coffee in your mug and you place the mug on a table, eventually it cools down. And that's because of this transfer of all these molecules. The molecules in the hot coffee begin to come out into the atmosphere. And the surrounding molecules go into the coffee to cool it down. The heat transfer from the coffee to the surroundings stops when the two reach the same temperature. So eventually, when the temperature between the atmosphere and the coffee is the same, then it's reached thermal equilibrium. At thermal equilibrium, there is no additional transfer of heat. So heat is completely constant. When a system absorbs heat, its temperature changes. Heat absorbed by a system and its corresponding temperature change are directly proportional. So the way that they're interacting is directly related. The constant proportionality in the system is its heat capacity. And heat capacity, which is C, is a measure of the system's ability to absorb thermal energy without undergoing a large change in temperature. So we want to know the capacity of something to absorb heat by just maybe 1 degree Celsius. That's heat capacity. So the quantity that's required to change heat or needed to absorb by just 1 degree Celsius. So just a really, really small change to kind of think of it as a constant. When you place a saucepan on a kitchen flame, completely empty, right? You just put a pan on the flame. Its temperature rises quickly. It actually gets really, really hot. So a lot of people actually like to, or maybe me personally, I learned this as I got better in cooking, is I would put my pan on the stove and I would just let it warm up a little bit so it's already ready when I'm making eggs or something or pancakes or whatever, because the pan itself already has a high temperature. Now, if I were to add water, do you think that the temperature would go up just as fast in my saucepan? No, right? It's going to be a little bit more slow because you're adding a lot more matter. So there's more matter, there's more substance to absorb heat. So it's going to take longer. So when you add the water, the same amount of heat must now warm the saucepan and the water, so the temperature rises a lot more slowly. And this tells you that heat is an extensive property, so it depends on the amount, right? Little bit of coffee, a lot of coffee, little bit of water, a lot of water, no water. They're all going to affect the temperature. The less you have, the more the temperature is going to rise. So it depends on the amount of matter being heated to know exactly how much heat has to be absorbed. So water is more resistant to temperature change than steel. Water has an intrinsically higher capacity to absorb heat without undergoing a large temperature change. So the measure of the intrinsic capacity of a substance to absorb heat is called its specific heat. So when you see C sub S, you're talking about specific heat, which is the amount of heat required to raise a temperature of 1 gram by 1 degree Celsius. So your units for specific heat are always joules per gram degree Celsius. Now we can also have the molar heat capacity, which is the amount of heat required for 1 mole per degree Celsius. So it tells us how much is being absorbed by just that small mass or mole change and small temperature change. So it's a constant. It's a way that we can kind of take it into account and control what's going on. Now, I want you to notice what's in these units. We have joules, so heat, grams, mass, and temperature. So if I just wanted to know the heat of a substance, I can use these different values with the specific heat to determine that. Which brings us up to the heat equation. So heat, which is Q, is equal to mass times specific heat times change in temperature. Change in temperature will be T final minus T initial. Best way to look at this equation is to do a problem. So how much heat, so you're looking for Q, is required to warm 15 liters of water from 25 degrees Celsius to 100 degrees Celsius. So my T initial is 25 degrees Celsius. My T final is 100. The density is 1 gram per milliliter. So Q is equal to MC delta T. MCAT is what I usually call it. Now, C, unless you're solving for it, you can always look it up. So since it's not given to you in the problem, you would look in your book, and there's a table of specific heats. We are talking about water. So you would look up the specific heat of water, which is 4.18 joules per gram degree Celsius. Well, now I have my mass and, don't have my mass yet. I have my specific heat and I have my change in temperature. How can I find my mass since this is what I'm looking for? Well, I have my volume and density, and I know that I can use volume and density to get mass. So if I take 15 liters and convert to milliliters, and then convert to grams, so there's 1,000 milliliters in a liter, and 1 gram per milliliter for this density. Milliliters cancel, liters cancel, and you're left with 15,000 grams. Then you can plug everything in. And you can check your units. Your grams cancel from your specific heat. Your degrees Celsius cancel. So here, this is how you can use specific heat to get heat, right? To get the unit of heat. And if we plug that into the calculator, what do we get? So 100 minus 25 is 75 times 4.18 times 15,000 is 470,250. Now notice how this is a really big number. Q is usually in kilojoules, so we usually want to convert this to kilojoules to get a better idea of how big or small this is. So if you divide this by 1,000, you have still a pretty large number. And how many sig figs do we want? 3, so 4.70 times 10 to the third kilojoules. Alrighty. Now, let's practice another problem. I'm going to set this up and then I want you to try this on your own. Suppose you find a penny, 3.10 grams, so you have mass. How much heat is absorbed by the penny as it warms from the temperature of the snow, which is -8, so that's my T1, Ti initial, to the temperature of the body, Tf. What am I looking for? How much heat is absorbed? So I want Q. So I know Q is equal to MC delta T. I want Q. I have my mass. I have my change in temperature. So I need to look up C. Now, where would I look up C? If it's not given to you, again, you can look it up in your book. And is it of water? How do you know what specific heat you're looking for? Well, it's penny, right? So you're looking for the specific heat of the penny. So you'd look at your table and you'd find it, which is 0.0385 joules per gram degrees Celsius. You'd plug everything in and you would get your answer and round to the proper sig figs. So now this brings me up to thermal energy transfer. So when you have two things happening, basically. So think of, if you put a metal, right, like a hot metal, into water, what happens to it? So this is an experiment I actually have done in my Intro to Chem class to kind of observe this behavior. You take a metal and you clamp it, and you then light a Bunsen burner. And you put this metal on top of the Bunsen burner, so you're just really, really warming it up. Sometimes you can even put it in a test tube and warm up the test tube, but usually you just do directly the metal because you don't want the test tube to crack. So all of a sudden this metal is super, super, super hot. And then what you do is you place this metal into a cup of just regular room temp water. What's going to happen? Well, the metal is going to cool down, right? And the water is going to warm up. And that's going to happen for a while. Eventually, that's going to stop. When does that stop? Thermal equilibrium. So the molecules of the metal are going to go into the water to cool it down. To warm it up. And the molecules of the water are going to go into the metal to cool it down. This transfer happens continually until they reach thermal equilibrium. Now, at thermal equilibrium, there's no more heat transfer. Nothing changes with heat anymore. It's constant. So when the two substances at different temperatures are combined, the thermal energy flows as heat from the hotter substance to the colder substance. And if we assume that the substances are thermally isolated from everything else, so we don't take into account any other surroundings, we're just thinking of those two substances, the system and the water, then the heat lost by one substance exactly equals the heat gained by the other substance. So we would think of heat of the system exactly the inverse of heat of the surroundings. The best way to kind of think of what happens here and how to use it to solve a problem is to think of an actual example. So a 32.5 gram cube of aluminum, initially at 45.8 degrees Celsius, is submerged into 105.3 grams of water at 15.4 degrees Celsius. So you have your cup of water, and the mass of the water is 105.3 grams. And it's initially at 15.4 degrees Celsius. You then place this metal inside, which is 32.5 grams, and it has an initial temperature of 45.8 degrees Celsius. So it's much hotter than the water. What is the final temperature of both substances at thermal equilibrium? Aluminum and the water are thermally isolated from everything else. So that means that the system, which is the metal, is the inverse of the water. So since they're constant, what I'm going to do here, because I want temperatures, I'm going to define Q, since Q isn't going to change. So then I have my mass of my metal, my specific heat of my metal, and my change in temperature of my metal is equal to my mass of water, specific heat of my water, and change in temperature of my water. Now I'm going to take a moment and define change in temperature. I know change in temperature would be T final minus T initial. Now, T final, is that going to be the same for both? Yes, because of thermal equilibrium, they reach the same final temperature. So if we plug everything in but delta T, that means we would have 32.5 grams. And I'm not given my specific heats here. So for first, I would have to look up my specific heat for aluminum, which is 0.903 joules per gram degrees Celsius, times my change in temperature, which I'm going to leave like this. I'm going to define that that's aluminum, negative my mass of my water, 105.3 grams, specific heat of water, 4.18 joules per gram degrees Celsius, and then delta T of water. So now, if I do this math, right, if I multiply through, I have 29.348 on this side times delta T of aluminum is equal to negative 440.15 times delta T of water. So then what I can do is I can divide over my 29.348. That gives me negative 14.998 delta T H2O. And then now I'm going to expand what that is, right? So I know that this is T final minus T initial, which is equal to negative 14.988 times T final minus T initial, right? And I know that T final is going to be the same for both. So T final is then equal to negative 14.998 TF, so I'm going to expand this, plus 14.998 Ti plus the Ti of aluminum. So then, I'm running out of room here, but you would plug in all your values, right? You know that this would be of water, which is the 15.4, so you multiply that together, and your T initial is 45.8. Multiply that, add that number together, divide by 14.8, get that over to the other side, and then T final would be, I'm kind of skipping this because this is algebra, 17.3 degrees Celsius. Now, you can always solve this differently as long as you get here. So knowing that when everything else is isolated, you can define your system and your surrounding. They have to be equal, and at the thermal equilibrium, the heat is constant. So then you could solve for the mass of the metal or the water, the specific heat, the initial temperature, just knowing that they're equal to each other and one is inverse. So now we go to pressure. So that was all quantifying heat through the heat equation and then the thermal energy transfer. So taking a moment to quantify work. So we look at work as pressure volume work. And pressure volume work occurs when the force is caused by a volume change against an external pressure. So we know we've already defined work as a force acting through a distance. And now we're saying that it's the force caused by a volume that's against external pressure. So that's distance. So for example, the pressure volume work occurs in a cylinder of an automobile gas. The combustion of the gasoline causes gases within the cylinders to expand, pushing the piston outward and ultimately moving the wheels of the car. We can derive an equation for the value of pressure volume work from the definition of work as force by a distance. So if we look a little bit more specifically, what do we say for work and force? So when the volume of a cylinder increases, it pushes against an external force. The external force is the external pressure, which is defined as force divided by area, which we can then rearrange and say force is equal to the external pressure times area, right? Because it's the amount that's pushing against. So then if I go back to my work definition, which is force times distance, I can say that the work is equal to my external pressure times my area that it's going against times distance. Well, the distance through which the force acts is the change in height of the piston as it moves during the expansion, so the amount that it's going. So that would be substituting the density with the change in the height, right? So going that the change that it's pushing against is the change in height, which would then be that the work is equal to the external pressure times the area times the change in height. Well, the volume of a cylinder, as you can see here, is the area of its base, so the area here, times the height. That's just what we say for the volume of definition, or volume times distance if we kept it as distance. So then, since volume is equal to area times distance, or area times change in height, we can say work is then equal to the external pressure times volume, or change in volume is what I should say. So now we're still missing a part of it. So we have to think of the fact that work is done by expanding gases. So when the system is doing work, work is negative, right? And to make this equation negative, we actually have to add the negative sign in front of our variables. And why would it go in front of the pressure? Well, since work is done by the system, the expansion of the gas is doing the work, work needs to be negative. But upon the expansion, we know that the final volume is greater than the initial volume, so delta V, right, the change in volume has to be positive since this V2 is higher than V1. So change in V is always positive. So in order for W to be negative, the work to be negative, for a positive expansion, we have to add our negative sign in front of the external pressure. So the work caused by the expansion, right? So if we look here, the work caused by the expansion of a volume is a negative of the pressure that the volume expands against multiplied by the change in volume that occurs during the expansion. The units of the work obtained by using this equation are those of pressure multiplied by volume. And when you convert liters and volumes, we use a joule. So 1 liter atmosphere is actually equal to 101.3 joules. So another important conversion. So here again, you can see that the volume is equal to the area times the height difference, which we then said was volume times that external pressure, since pressure is equal to force and area. So that's how they all connected. And that's how we derive pressure volume work. So let's do a group check here. How much work is required to expand the volume of a pump from 0 liters to 2.5 liters against an external pressure of 1.1 atmospheres? So I have my P external, 1.1 atmospheres. I have my initial volume of 0.0 liters, and I have my final volume of 2.5 liters. I'm looking for work. Work is equal to negative P external change in volume. So then work would be negative 1.1 atmospheres times 2.5 minus 0.0 liters. So therefore, work would equal what? Negative 1.1 times 2.5 is negative 2.75 atmospheres, liter atmosphere. And we want work always in joules. So then we have to convert, which would be 101.3 joules over 1 liter ATM. So work is then equal to negative 278.575 joules. We want to sig fix, so I would say work is equal to negative 280 joules. And now because of the sign, if I asked you an extra conceptual question and I said, is work done by the system or onto the system? Work done by the system. Good. Alrighty, our last little bit for today. So what I want you to do is I want you to work through this question on your own. A 31.1 gram of pure gold, initially at 69.3 degrees Celsius, is submerged onto 64.2 grams of water at 27.8 degrees Celsius in an insulated container. What is the final temperature of both substances at thermal equilibrium? So this is a similar question as before. I want you to try this on your own in your worksheet. So last section of the day is going to be calorimetry.